Too much further into working with polar coordinates than what we already talked about 2 days ago, but I think it's good to hear the same thing again. Um, if it was confusing, the first time I said it, maybe here in the second time, try to say it a little bit different or explain it a little bit differently, so we're all kind of on the same page of what polar coordinates are, because they are the foundation for what we're going to do in the next chapter and a half. Okay, the next 4 weeks essentially. Are using polar coordinates and the foundation that they set is going to be very important. I guess the connection is if I were to ask you, how do you go from 0, 0? How do you go from 0, 0 to point A? Okay, you're probably going to tell me you move to the right 4 units and then up 4 units, correct? You move in horizontal directions and vertical directions. Okay. Now, like we said on Tuesday, or I guess it's Monday, you can move right 2, up 1, right 2, up 3. It's still going to get you to A. But all of those individual movements were also horizontal or vertical, right? Okay. The one thing about this is that in the Cartesian plane, it's one of the things that is really nice about it, is that that point is identified with one set of coordinates, and that is the only way that I can identify that point, right? Okay, I can't name, obviously name it anything I want to, A, B, C, D, but in regards to its ordered pair, I cannot write it any different, okay? Because the instant that I change that first 4, I now go to a different location, right? The instant that I change the second 4 to something different, I go to a new location, and that's the nice thing about the coordinate plane. It's kind of a one-to-one thing. Every point has one ordered pair, and every ordered pair is associated with one point, right? Does that make sense? Okay. That's how our number line works, right? Okay. But the Cartesian plane, the xy axis, the rectangular system that we put in here, is simply just a way for us to reference that location, that point A, in that two-dimensional space. Does that make sense? Okay? That point A is that spot, no matter what we overlay on top of it, it's the exact same spot. But what we overlay on top of it tells us how we're going to name that spot. Is that going to make sense? Or provide directions to get to that spot from somewhere. We put anything over this we want to. Okay, and the way I like to think about your coordinate systems is that they're transparencies. Okay, and I slap a grid on top of it, and now I've got kind of a roadmap to get from point A to point B or something like that. So with polar coordinates, that's all we're doing. Okay, we are going to change the grid to now being circles and rays that emanate from what we call our pole. Okay. The pole is the intersection. If we overlay our axes on top of them, and usually our axes are still there, but we overlay our axes on top of them, and now we've got our pole at the intersection of those axes. Okay. And our polar axis is going to be the positive x-axis. That's what we refer to those components as. So point B is the pole, and that orange ray is the polar axis. Okay. And now the way we talk about how we go from the pole to point A, instead of moving horizontally and vertically, what we're going to do is we're going to be on some circle, okay, and we're going to trace out some arc, okay, trace out some angles. That kind of makes sense? So now we're talking about how much does that ray have to move counterclockwise off the polar axis to get to A. So what we're interested in here is what is, I need another point here to do this, but we're now saying that we're interested in that 45-degree angle. We've now traveled in a 45-degree direction, and now to get to A, we need to know, okay, if I'm kind of a bird's eye view, standing at the pole here, okay, and somebody tells me walk to A, they're going to say, okay, walk at a 45-degree direction, and then I need to know how far I need to start walking, right? Okay, so the distance that I walk is the length of that segment right there. So see, this thing will give me length. That's for length of that. B to A. And I would walk 5.66 units on that ray at a 45-degree angle, and that's going to get me to A. Does that make sense? And that's exactly the same thing as walking gets me from my beginning point to my end point. It would be the exact same thing in the Cartesian plane or the rectangular system as walking to the right 4 and then up 4, right? But here's the nice thing. If I walk to the right 4 and then up 4, how many units did I walk? 8. If I start at B and I go straight to A along that ray, that we'll call that a vector ultimately. If I do that, how many units did I walk? 5.66, right? A little bit more efficient doing it this way, correct? In regards to distance traveled or something like that, okay? Those of you that have taken physics, maybe you've talked about vectors, right? Okay? This is going to lay the foundation for us to talk about vectors, okay? But that's how we identify that point right there. Let's see if I can get the name on here. Okay, so 4, 4, and that's if we're looking at the rectangular system, moving to the right 4 and then up 4. But that point can also be written as 5.66 comma 45 degrees. Okay, and hopefully with that diagram, you're seeing where the 5.66 comes from and where the 45 degrees comes from. Okay, but it's just simply a set of directions to get you from a starting point to an ending point. Okay, just like they were, just like your Cartesian coordinates were given in Algebra 1 to get from 0, 0 to any other point. Okay, does that kind of make sense? Okay. Now, what is kind of nice, but also kind of bad in regards to the requirements that we have and the understanding is that, I call that circle right there, that point, its location is defined by 6 comma 30 degrees, right? And I think I showed you guys on Monday, if I take another point like D, okay, and say, well, D started there, but it went all the way around this circle, and it came back there, how many degrees would it have traveled? 390, right? If I type in, just say that, so just say D is equal to, we'll go 6 again for the radius, but then type in 390 degrees, it plots it on the same point. You see how it highlighted it, right? Change the color. I mean, we see that D is on top of A, okay? If I say that I want to deal with, I guess we got those two colors. Let's say we want to take point E, okay? And I want to say it's 6, comma, let's go 30 degrees. We'll do it this way, it'll be easier. 30 degrees plus 360 degrees. So that'd be 390, right? Plus 360, plus then 360, plus then 360. Let's do one more. Kind of silly, but you're seeing the pattern here. I'm just adding 360, right? Put my degree on there. Where's that point going to go? Same spot. Okay. Now you can see here that GeoGebra actually does the convenient math that we would want to eventually do. Whatever that angle was, it was up into like the thousands or whatever. We wouldn't want to deal with that, so we would convert it down to the smallest coterminal, positive coterminal angle possible, which is 30 degrees. But there's an endless way of labeling in regards to the direction and the radius of that point. Does that make sense? Okay. In another one of those kind of endless ways of doing that is actually one thing that people struggle with a lot. And it has to do with essentially taking that orange ray and extending it through the pole so that it goes in the opposite direction. So now I have an opposite ray. Does that kind of make sense? Okay. If I look at that black ray is highlighting what ends up being the 210 degree marking on the unit circle. Does that make sense? Okay. So if I were to trace out from C this direction all the way up to there, that'd be 210 degrees because that's 30. So that's got to be 30 vertical angles, right? Okay. So I could actually say that, let's just call it point F. Let's say that it is at, now instead of 6, I'm going to write -6. Okay, and I'm going to write 210 degrees. Where did it take F? Took it, come on. Oh. Took F and put it right there, correct? Same spot A was, okay? So that logic kind of maybe gets us to realize, one, there's a lot of different ways you can name the same point, which is a nice thing, but at the same time, it's kind of a bad thing, okay? Because bad in regards to, you might do it and label it as 6, 30, and your neighbor labels it as -6, 210, and you working together might say, well, one of us is wrong, or you're both right. Does that make sense? The nice thing is that you're both right, but the bad thing is if you don't understand this is a possibility, you might think one person is wrong over the other. All right, so I kind of want to talk about how we structure that process for being able to identify points, okay, in the polar plane. So can I talk about this on Monday? Okay, so the center of the graph is called the pole. We got the polar axis.
On Jupiter, I saw that when I did it on the regular plane, it used a comma, but then when I use it as a semicolon, do we use a semicolon?
You can if you want to, but I think that is just, I've never seen it. I have to go back through. I'll grab my, it's called, the course that you do a lot of this stuff with in college is called complex analysis. Analyzing the complex plane. That's basically what this stuff's for. Or one of the applications is. I'll go through that textbook and see if there's any other different notation, but I think for the most part it's just a comma.
Okay.
If you want to put a semicolon, that's fine.
Okay.
But I think it is just kind of, the semicolon is like GeoGebra's way of knowing to plot it in polar instead of rectangular. So we got our polar axis being that thing right there. Okay. We talked yesterday or Monday, I guess. Every point is labeled as an r comma theta, where r is obviously the radius or the circle that your point is lying on. Okay. And theta is the angle that you are going to kind of move around that circle. Okay. So if I'm going to plot the point 5 comma pi over 4, I'm going to find the pi over 4 angle. Okay. And so that provides that ray, right? And usually the rays that are emanating from this thing are 15 degrees or 30-degree increments. Okay, they can be 1-degree increments, but it's kind of like the rectangular system. We usually use 1 integer increments, right? Go 1, 2, 3 in both directions, positive and negative. But you know that 1/2 is on there somewhere. You know that 2/3 is on there somewhere. You can kind of ballpark those things, right? So 22 degrees is up there. I just got to ballpark where it's at. Okay, which might be a little bit more difficult than working in the rectangular system, but it is something we occasionally have to do. Once I find the angle, then I just travel out 5 units on that angle. There are 5 circles on that ray, and that's the point 5 comma pi over 4. Okay. Now, there are, like I said, an endless ways of naming that point, so I'll show you how we do this with a negative angle. A negative angle means we just travel in the negative direction like we always have, and in the clockwise direction. So if I have 3 comma negative 3 pi over 4, I'm going to travel in that direction 3 pi over 4 radians. So that would give me that one right there. Okay. Now you see the chart that I'm using here labels that as 5 pi over 4, correct? Is that 5 pi over 4 going that direction? They're coterminal, right? Okay, so that's fine if you want to label it that way. So 3 comma negative 3 pi over 4 is going to be the exact same point as 3 comma 5 pi over 4. Because what do you get when you add 2 pi to negative 3 pi over 4? 2 pi is 8 pi over 4, right? Negative 3 pi over 4 plus 8 pi over 4 should give you 5 pi over 4. So if you want to rewrite this point, we can do that in a moment. But I would go then out 3 units on that, and there's my point. So that's 3 comma negative 3 pi over 4. Some of the algebra that we might do with these points later on, the negative might be something that you don't like. Some people don't like dealing with double negatives and stuff like that, right? Or subtracting a negative. So if I wanted to, before I did any work, I could change that point to 3 comma 5 pi over 4 just by adding 2 pi. Okay? So using that coterminal relationship that we've talked about for about 2 months so far. Now, it's a little bit more kind of convoluted when I want to deal with a negative radius, when the r value is negative. Okay? What you're going to do is you're going to go out to 2 pi over 3. You're going to go out to your angle. Okay? And this is kind of the reason why in the directions it tells you to always do the angle first, because in a situation that it's a negative radius, it makes more sense to do the angle first. So I'm going to go 2 pi over 3. So that would be that ray right there, right? Okay? Now, if I went out 4 on that, that would mean that I plotted the point 4 comma 2 pi over 3. I don't want that. I want negative 4 comma 2 pi over 3. So what we do is we extend that ray through the pole. We extend the 2 pi over 3 ray through the pole, and that's what that dotted orange ray is doing. Okay? And now on that dotted orange ray, there's where I count out 4 circles. Okay? And that point there would represent the negative 4 comma 2 pi over 3. Okay? Now, I'm a person, like I said, I don't necessarily like negatives. I can deal with them if it's necessary. But if I look at this, point here, and let me actually, be easier if I end the PowerPoint, if I can. Seems as though everything is froze. There we go. Fabulous. All right, so if I'm looking at that point, negative 4, 2 pi over 3, is that the same thing as traveling that direction? Pi over 3 units, right? So I could actually name that with a positive angle, a negative angle, negative pi over 3. But now if I went negative pi over 3, I don't have to extend going through the other side of the pole, right? Okay, so that point I could say is 4 comma negative pi over 3 if I wanted to. Okay, does that make sense to everybody? But let's say I don't like the negative angle as well. Okay, well, could I add 2 pi to that to get back to it? So negative 4 comma 2 pi over 3 could actually change to 4 comma 5 pi over 3, and that will be the exact same point. Okay, and I'll use GeoGebra to kind of prove this. If I plot, what was it? Started as negative 4 comma 2 pi divided by 3. GeoGebra was having problems with what the 2 pi over 3 is. So let's do it this way. Let's see. Oh, maybe I did it this way. Maybe, yeah. There we go. So there's as polar coordinates. Okay. There's that point. Okay. But it is the same thing as we'll pick up with this tomorrow.
Have a great day.
Thank you, too. So point A is the same thing as 4 comma 5 pi over 3. It is the same thing as for, I think we did comma negative pi over 3. Okay. Those are all acceptable versions of negative 4 2 pi over 3.